Welcome to the XRF Micro XRF product demonstration. Easily adapted to most any scanning electron microscope. Simply attach the Micro XRF addition to any workable port with the correct geometries. Two vacuum interlock sensors are provided for safety along with a warning beacon, and then control panel. An EDS detector is required along with the XRF EDS system for optimum performance. Here is the Micro XRF optic, and then the EDS detector. Sample is presented, X-rays are emitted from the Micro XRF optic, then collected from the sample with the EDS detector. Let's take a look at some BS38C tools still using both techniques. First, the E-beam from the electron microscope. The SEM is evacuated, then voltage is applied to the sample. Here we see the E-beam excitation of the trace elements. Very small peaks for 0.28% concentrations. Now let us see the Micro XRF on the same sample. X-rays on, beacon on, and visualize the actual excitation spot where the analysis takes place. With Micro XRF, you will notice tenfold the peak heights and sample sensitivities. Now let us examine the NIST 610 forensic glass sample. Only XRF offers combined E-beam and Micro XRF in a single quantitative application. First, the E-beam excitation for the sample is acquired, only collecting the light elements for the lower kV range. Once the lighter element have been acquired, the XRF X-beam is activated, warning beacon is on, then the higher energy X-rays are acquired. As we can see, all of the low ppm trace element are easily observed using the XRF X-beam. This enables the SEM scientist to be able to see all the element in any sample. Only XRF combines the two excitation methods into one single quantity. First, the E-beam spectrum is processed. Then the Micro XRF spectrum is processed, which combines both excitation techniques into a single analysis. Now we will demonstrate the ability to perform elemental X-ray maps using both excitation techniques. For this applications we use a new ultra-fast superstage. Sample moves under both beams, collecting carbon with the E-beam and zirconium with the XRF beam. Five kV from the E-beam and higher Z element from the Micro XRF beam are combined. Now we will demonstrate overlaying X-ray element maps from both excitation sources. Carbon, from the electron beam. Zirconium, from the XRF beam. And iron, from the XRF beam. Now, let's view some microelectronic applications. The sample is moved under the excitation sources using a motorized stage. Composition multi-element map. Then, only the element LED is displayed. With deeper penetration from XRF, we can look closer at the solder laid down on the lead frame. Titanium map, with the addition of nickel, and then bromine. This is our optical image of a circuit board, then converted to a X-ray map. Trace bromine added, then lead, then copper, and silver. Pipe scale. Silicon. Chlorine added, and iron. Then copper. Concrete analysis. Calcium. Then potassium. Manganese only. Then magnesium. And carbon. Geological samples. Electron beam map. Micro XRF. Cat's eye quartz. Nickel. Then manganese. And molybdenum. And iron. Fossil analysis. Analyzing a trilobite. Trace iron. Dinosaur bone marrow. EDS map. XRF map. How about a fossilized nautilus? And here, we have a fossilized shrimp with calcium and then iron. In the forensic community, glass and paint chip analysis with micro XRF is commonplace. Applying micro XRF to the scanning electron microscope combines two technologies into one integrated unit. This means you can analyze most all elements, in all samples, at the same location, at the same time. Stability, accuracy, and sensitivity are all increased with the addition of micro XRF to NESEM. Existing customers.